Hi, this is Dr. O'Connor. Today we're going to talk about compounds that have oxygen, sulfur, or halogen. So the first thing we're going to talk about are the alcohols. And the alcohols look like this. So you have some alkyl group here, some organic group, and the hydroxyl group. Okay, so first we're going to talk about some common alcohols. The first one is called methanol or methyl alcohol. And here's the formula right here, but let me go ahead and draw the structure here. And it looks like this. So we have a carbon atom, in this case bonded to 3 hydrogens, and the hydroxyl group here. So a little bit about methanol. It is colorless. It mixes with water. Actually, it's miscible with water. It's very toxic to humans when you ingest or inhale it. In fact, in very low doses, around 15 milliliters, it will cause blindness. In higher doses, about 100 to 250 milliliters, it can cause death. Methanol is used industrially as a starting material for the preparation of formaldehyde and an ether, MTBE, that's methyl tertiary butyl ether, and many other uses for methanol. The next alcohol that we're going to look at, it's very common, is ethyl alcohol or ethanol. Notice the 2 carbons, so we can draw that structure like this. So we have the carbons and the hydroxyl group here, and of course these are the hydrogens. So we all know, I think, that ethanol is produced by fermentation of grain and sugar, and is sometimes called grain alcohol. It's present in wine, about 10 to 13%, could be a little bit higher in beer, 3 to 5%, and also in liquor, so anywhere from 35 to 90%. If we have 100 proof, that means it's 50% alcohol. So a bottle of vodka, for example, that is 80 proof, that would mean that it is 40% ethanol. Most ethanol is produced by hydration of ethylene. 100% ethanol is called absolute alcohol. Gasohol, as we know, is a blend of ethanol and gasoline. The next common alcohol is what we call a dialcohol, and that is ethylene glycol. There are 2 OH groups. In fact, let me go ahead and draw this. So let me draw these CH bonds here, and notice that we have an OH group bonded to each of the carbons. And this is a colorless liquid. It's also miscible with water, as is methanol and ethanol. Insoluble with nonpolar solvents, used as an antifreeze and as a starting material for the production of polyester films and fibers. And it's also a central nervous system depressant. So a dose as small as 100 milliliters could be lethal. In fact, dogs are attracted to antifreeze, and yet the antifreeze is very toxic to them. The next one that we want to take a look at here is a trialcohol. So that means we have 3 hydroxyl groups, and that is glycerol. And I think we've all heard of glycerol or glycerin. So here we see 1, 2, 3 hydroxyl groups. This is also a colorless liquid. It's miscible with water, meaning that it mixes in all proportions. It is not toxic. It does have a sweet taste to it. And we find this in candy and prepared foods. We find it in cosmetics, plastics. It's also used in antifreeze and used as a solvent. Later on, we're going to talk about glycerol when we get to the biochemistry portion, and we're going to find that it provides the structural backbone of fats and oils. So we'll talk about glycerol again a little bit later. Now, what we want to do first, as usual, when we start these chapters, we start with the nomenclature, properties, and then reactions. So to name alcohol, again, a lot of them are known by their common names, but I'm only going to hold you responsible for the IUPAC naming. So the first thing you do is find the longest continuous carbon chain that contains the hydroxyl group and name the parent chain using the alkane name only, and then replace the E in the alkane with OL. If the compound is cyclic, add OL to the parent name of the cycloalkane. Number the chain from the end nearest the OH group. You want the OH group to have the lowest possible number. So that has priority over any substituents. Once you have the OH group numbered, then you number the other substituents according to the OH group. So let's go ahead and name some of these alcohols. So let's name the following alcohol using the preceding rules. So the first thing I do is I find my longest continuous carbon chain that contains the OH group. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a nonane. So we replace the E in nonane with an OL because we have an alcohol. And I numbered from left to right. My OH group is on carbon number 2. If I were to number from right to left, my OH group would be on carbon 8. So we want it on the lowest possible number. So what we have here is a 2 nonanol. And then on carbon number 5, we have 2 methyl groups. So what we have here is a 5. Actually, this here is missing the 5. So what we have here is a 5 dimethyl 2 nonanol. Okay, so that's how we name that. Here it says draw a structure corresponding to the following name. So we have a 2,3,7 trimethyl cyclooctanol. So we draw this 8-member ring, okay, and when we name these cyclic alcohols, you want, again, that OH group, the hydroxyl group, to have the lowest possible number. So in this case, that would be number 1, carbon number 1. So you would go ahead and number that as 1. And then I can either number this way 2, 3, 4, 5, 6, 7, 8, or I can number this way where I have 1, 2, 3, 4, 5, 6, 7, and 8. So if I number counterclockwise, my first methyl group is on carbon 3, and then I would have a methyl group on carbon 7 and carbon 8. But if I go clockwise, then I have methyl groups on carbons 2 and 3 and 1 on 7. So I want to name this as 2, 3, 7 trimethyl, tri because I have 3 methyl groups, cyclooctanol. So rather than cyclooctane, that'd be cyclooctanol. Replace the E with an OL. That's how you name the cyclic alcohols. Now, let's go up here. Let's name this alcohol right here. So again, I want to start at the end that is going to give the OH group the lowest possible number. So this would be 1, 2, 3, 4, 5, 6, 7, 8. We'd name that as an octane, but we have an alcohol, so this is an octanol. So octanol. and the OH group is on carbon number 2, and we have a methyl group on carbon 2, 3, 4, 5, 6, 7, and carbon 7. So this would be a 2,7 dimethyl 2-octanol. Now, I want you to practice naming those alcohols. There are plenty that you can practice in your book. When we have a dialcohol, we call it a diol or a glycol, okay? And so a glycol is a dialcohol or a diol. So the numbering starts from the end closer to one of the OH groups, and the diol name ending is used. So for example, this one here, we already know the common name is ethylene glycol, but the IUPAC name would be, well, we have an OH group on carbon number 1 and an OH group on carbon number 2, and we would call this 1,2 ethane diol, to show that that has 2 OH groups. This one here, let's go ahead and start numbering. If we start numbering this way, 1, 2, 3, we have an OH group on carbon 2 and 3, but if I number this way, I have an OH group on carbons 1 and 2. So we want to name this as a 1,2. We have 1, 2, 3 carbons here. That's a propane diol. So 1,2 propane diol. Now we can classify alcohols as primary, secondary, and tertiary. Okay, so what you do is you look at the carbon that is bonded to the hydroxyl group, and if it has one alkyl group, or look at it this way, if it has 2 hydrogens, then this would be a primary alcohol. A secondary alcohol would be bonded to these 2 alkyl groups, and it would have 1 hydrogen. This is a secondary alcohol. A tertiary alcohol, on the other hand, would be bonded to 3 alkyl groups, 3 organic groups here, and the OH. So in other words, that is a tertiary alcohol. Let's take a look at some properties of alcohols. Small alcohols are more polar than hydrocarbons. Okay, remember hydrocarbons are not polar at all, but our smaller alcohols with 4 or less carbons are water soluble, and once we get to about 4 carbons, we start seeing the solubility decreasing. By the time we get to hexanol, hexanol is not soluble in water. Remember, if something is not soluble in water, it's nonpolar. Let's take a look here. Methanol, as we found out before, is completely miscible with water. It's very polar. Ethanol is also very polar. Propanol is polar. Okay, once we get to butanol, like this, okay, 4 carbons, now this is going to become less soluble. Okay, and then of course when we get to, let's say, hexanol, 1, 2, 3, 4, 5, 6. Now this is going to be insoluble in water. This would be considered nonpolar. Think about it. You have this very, very large hydrocarbon chain and then this small OH group. So this is going to have more hydrocarbon character than something like methanol or ethanol. So the smaller alcohols will dissolve in water, but the larger ones will not because they're more hydrocarbon-like. Your alcohols are capable of hydrogen bonding. Remember, to hydrogen bond, what you need is a hydrogen bonded to an oxygen, a fluorine or a nitrogen. So alcohols can hydrogen bond. Straight chain alcohols up to 12 carbon atoms are liquids, and each boils at a much higher temperature than a related alkane. They have higher boiling points. Methanol and ethanol are more like water in their properties, and they of course, are miscible with water, and the reason why is because they form hydrogen bonds with water. And both methanol and ethanol can dissolve small amounts of salts. Alcohols are also miscible with organic solvents. Alcohols with large organic parts, like I just said, are going to act more like alkanes or hydrocarbons and less like water. So you got to keep that in mind, the size of the molecule. Here I have a question. Glucose is much more soluble in water than 1-hexanol. Both contain 6 carbons. Why is this? Well, let's look at 1-hexanol. 1-hexanol is not soluble in water. And what you have is you have this long chain, this long hydrocarbon chain with the OH group. This is going to be more hydrocarbon-like. But glucose, yeah, it has 6 carbons, but it also has 1, 2, 3, 4, 5 hydroxyl groups. So yes, it's going to be soluble in water. There are more opportunities here for the hydrogen bonding, okay, to occur with a water molecule. So that's going to make it more soluble. So like, for example, right here, I'm going to form a hydrogen bond with water, okay, and here and here. And even right here, this oxygen here, it has the 2 lone pairs. It can also, there can also be a hydrogen bond form between a molecule of and this oxygen. So yeah, this is going to be very soluble in water, where this, again, will act more like a hydrocarbon or an alkane. We're going to look at some reactions of alcohols. And the first one we're going to look at is what we call a dehydration reaction. This is actually the reverse of what we talked about before when we discussed alkenes. Remember, we talked about the hydration of alkenes. Well, dehydration is the loss of water from an alcohol to yield an alkene. Remember, the hydration was we would add a molecule of water to the alkene to produce the alcohol. This is like the reverse. We start off with an alcohol. So you have 2 carbons, right? You have your OH group here, a hydrogen here. We have to have acidic solution, usually sulfuric acid, a catalyst. And what will happen is this hydrogen here and the OH will combine to form water, and then a double bond will form between the 2 carbons. So we go from an alcohol to an alkene. For example, here we have a carbon with an OH group bonded to 3 methyl groups. Actually, let's go ahead and draw this out up here. And I'm just going to do the 2-dimensional structure here. And let's go ahead and name this alcohol. So what we have here is a 1, 2, 3 chain alcohol. We have a methyl group on carbon 2 and the OH group on carbon 2. So what we have is a propanol. And so we have a 2-propanol. The OH group is on carbon 2. And we have a methyl group also on carbon 2. So 2-methyl, 2-propanol. And what's going to happen is the OH group is going to combine with a hydrogen that's bonded to an adjacent carbon, okay, and those will combine to form water, and then we end up with a double bond here between carbons 1 and 2. So we convert the alcohol to an alkene via a dehydration reaction. Let's go back up here. Sometimes more than one alkene can result when an alcohol undergoes a dehydration reaction. So for example, let's take a look at this alcohol here. This is 2-butanol. It has 2 adjacent carbons, one on either side, that have hydrogens bonded to them. We know the OH group is lost, which hydrogen? One of these or one of these? Well, let's go ahead and draw this so that one of these hydrogens is lost. And so what we end up with is this butene here. So 2-butene. For the other product, we can draw it to where one of these hydrogens is lost and combines with the OH, and we end up with 1-butene. It turns out that the major product is 2-butene and the minor product is 1-butene. So both products will form, but one product is going to be the major product, and it's this 2-butene. Why? Because the major product in the dehydration reaction is going to be the one that has the greater number of alkyl groups attached to the double bonded carbons. So we look here, this double bonded carbon has one alkyl group. This double bonded carbon has one alkyl group for a total of 2 alkyl groups. Over here, this double bonded carbon has one alkyl group, and here this one has 0. So that's a total of 1 alkyl group. So the one that has the greater number of alkyl groups bonded to the double bonded carbon will be the major product. I want you to practice these types of reactions, these dehydration reactions. So what I have here is an extra credit assignment. It will be worth 5 points. You need to go ahead and write these structures for problems 1 through 3. And I want to know what alkenes will be formed from dehydration of these 3 alcohols. If more than one product is possible, then make sure you indicate to me which is the major product. For number 4, what I want you to do is I want you to tell me what 2 alcohols, well, there are 2 different alcohols that can yield 2-methyl-2-pentene on dehydration. So make sure that you have 2 alcohols to get credit for this. Problems 1 through 3 worth a point each, and then 2 points for number 4. You can do this, and you can slip this underneath my office door by no later than next Friday. Slide under office door no later, than next Friday. And next Friday is, wow, we're going to be in February by next Friday. That's going to be February. So if you need to, pause this video and get these structures down, get this copied down, just pause the video and get this to me by next week. We're going to look at some other reactions of alcohols. We're going to look at oxidation of alcohols. And the reason I want to look at oxidation is because these are the types of reactions that we're going to see when we get into the biochemistry. Before we go to the oxidation, we need to become familiar with a few terms and also some other compounds that we have not covered yet. It turns out that primary and secondary alcohols are converted to carbonyl-containing compounds when treated with an oxidizing agent. So what is a carbonyl-containing compound? Well, I might have something like this. And let's just assume hydrogens, okay, attached to these carbons. But here we have a carbon-oxygen double bond. A carbon-oxygen double bond is called a carbonyl group. So this would be carbonyl carbon, okay? The carbon-oxygen double bond functional group is a carbonyl group. Now, you already know what oxidations and reductions are. We talked in terms of oxidations. We can think of something losing electrons or an increase in the oxidation number. Reductions, the gain of electrons, or a decrease in oxidation number. In organic chemistry, you can think of oxidations as an increase of the number of carbon-oxygen bonds with a decrease in the number of carbon-hydrogen bonds. And of course, an organic reduction would be the opposite, a decrease in the number of carbon-oxygen bonds with an increase in the number of carbon-hydrogen bonds. So let me show you something here so that you can see what I'm talking about. Let's say that I start off here with an alcohol, okay? And let's say I'm able to react this alcohol, and when I react this alcohol, what I end up with is this compound here. Remember, these are hydrogens here. I'll go ahead and put these in for you. It's hydrogen. Whoops. It's a hydrogen. That's a hydrogen. Here we have one carbon-oxygen bond. But here we have a carbon-oxygen double bond. So we've seen an increase in the number of carbon-oxygen bonds. This would be an oxidation. Now, let's say we add oxidizing agent. I will represent an oxidizing agent with a capital O in brackets. Let's go ahead and see what happens here. So what if I end up with something like this now? So we have our carbon-oxygen double bond, and now this. So we see from here to here, the carbon-oxygen bonds have been increased. So this is an oxidation. Also notice that from here to here, we've decreased the number of carbon-hydrogen bonds while increasing the carbon-oxygen bonds. The same here. Those are organic oxidations. The reverse, okay, going from here to here, would be a reduction, a decrease in the number of carbon-oxygen bonds. And then the same here, going from here to here, that would be a reduction. We see a decrease in the number of carbon-oxygen bonds, but an increase in the number of carbon-hydrogen bonds. That's an organic oxidation and organic reduction. Remember, you have to have oxidation with reduction, or reduction with oxidation. Okay, you can't just have oxidation, or you can't just have reduction, because they happen simultaneously. Alcohols, primary and secondary alcohols, can undergo oxidation. So how does that occur? Here we have the carbon that has both the OH group and a hydrogen. That's the requirement for oxidation. The carbon that is bonded to the OH group must be bonded to a hydrogen. Okay? And again, here's our oxidizing agent. And one of the hydrogens will be removed from the OH group, and the other one from the carbon that bears the OH group. Okay? What'll happen is they will combine with an oxygen from the oxidizing agent to form water, and then a double bond will form between the carbon and the oxygen. Okay, so what we have is we have another, we've gone from a single to a double bond here, so we see that a new carbon-oxygen bond is formed and a carbon-hydrogen bond is broken. So that is how an alcohol is oxidized. Now, tertiary alcohols do not react with oxidizing agents. Why? Because a tertiary alcohol does not have the available hydrogen on the carbon that is bonded to the OH group. So tertiary alcohols do not undergo oxidation. So that's something that you want to remember. Only primary and secondary alcohols. Now, it turns out that a primary alcohol can be converted into either an aldehyde or a carboxylic acid. I'll show you what those are in a minute. So a primary alcohol we react it with an oxidizing agent, and what we end up with is an aldehyde. An aldehyde has this group here, a carbonyl group and a hydrogen bonded to carbonyl carbon. Now, that would be a gentle oxidation of the primary alcohol, okay? Now, if I add more oxidizing agent, this aldehyde can be further oxidized to a carboxylic acid. Carboxylic acid has this functional group here, a carbonyl group, and then bonded to the carbonyl group is the OH group. A very common carboxylic acid is acetic acid, and that looks like this. This would be acetic acid, okay? Full of an aldehyde would be maybe something like this. Okay, and again, as I said, it's that carbonyl carbon. We have this carbonyl group, and there's a hydrogen bonded to the carbon. Okay, so this would be an aldehyde. Secondary alcohols, on the other hand, are converted to ketones. Ketones also have a carbonyl group, but carbon is not bonded to a hydrogen. The carbon is bonded to these two alkyl groups. So an example of a ketone that you're all familiar with would be acetone. So again, notice that the carbonyl carbon is bonded to two other carbons. There is no hydrogen. This is a ketone, and this particular ketone is acetone. The secondary alcohol, again, is going to be oxidized to the ketone. So what we have is the carbon that is bonded to the OH group and a hydrogen. The hydrogen and this hydrogen combine with an oxygen to form water, and a double bond forms between the carbon and the oxygen, and we end up with a ketone. Okay? Again, tertiary alcohols do not react with oxidizing agents. Why? They don't have the available hydrogen atom, and we went through that before. Let's take a look here at a reaction. Let's do this one. Okay, so here we have an alcohol. Okay, and our oxidizing agent. And this happens to be called benzyl alcohol. Yep, that is one word. Okay, but let's go ahead and redraw this. I'm going to redraw it, and that's what you should do with these if you can't tell the structure just from looking at it. So let's redraw this. We have this carbon here with the two hydrogens, and then we have the OH group. This is a primary alcohol, so we have a primary alcohol, and what's going to happen is this hydrogen here is going to be lost, so is this one, and our product then is going to be an aldehyde because it's a primary alcohol, so we're going to end up with an aldehyde. Sorry, my drawings don't look that good. And so as I said, we're going to have one hydrogen. So here's the carbon, and what's going to happen is a double bond here. Okay, so this double bond is going to form here, and of course the hydrogen. So what we have here is an aldehyde, and this is actually called benzaldehyde. Okay, now if I add more oxidizing agent, now what's going to happen is we're going to end up with a carboxylic acid. Okay, So we add more oxidizing agent. We have the carbon with the double bond, okay, the carbonyl group, and then this OH group here. So this would be a carboxylic acid. So just practice some of these reactions. There's one in your book that you can do that involves a secondary alcohol. If you have any questions, you're more than welcome to contact me. The next group of compounds that we're going to talk about are phenols. And we've already been introduced to phenols in a previous chapter. And this is phenol. It's a benzene ring with one of the carbons bonded to a hydroxyl group. The IUPAC name, of course, is hydroxybenzene, and the common is a phenol. And phenols are also a class of organic compounds. So phenol was used as a medical antiseptic and also as a topical anesthetic. And it was also used in lozenges, like for sore throats. They don't use it as much anymore because phenol can cause severe skin burns, and it can also be toxic in large amounts. So most mouthwashes and lozenges only contain about 1.5% phenol. In fact, Listerine, if you look at the original Listerine mouthwash, it contains phenol. This one here is thymol, and obviously it's a phenol. We have the benzene ring with the OH group, and this can be used as a topical anesthetic, and it's found in the herb thyme. Alkyl substituted phenols, cresols, also we call them methylphenols, are used as disinfectants in hospitals for cleaning. So many phenols are used as disinfectants, okay? In order to name phenols, we go ahead and name with the ending phenol. So here we have a phenol with a chlorine, and the chlorine is in a para position. So this would be para, or P, chlorophenol. Here we have a phenol with a methyl group, and that's in a meta position. The methyl group is meta to the OH, so this would be M for meta, methylphenol. And then here you asked to draw a structure for p-ethylphenol. This is para, so we draw the phenol, and the ethyl is in the para position. Some properties of phenols. In this particular chapter, I don't expect you to know how phenols are prepared. I just want you to know how to name them, recognize them, the properties of the phenols, and we'll talk a little bit about the acidity. So phenols are somewhat water soluble, not very, because of that benzene ring. So they're not going to be very water soluble. They have higher melting and boiling points than similar substituted alkyl benzenes. They're very weakly acidic, and we're going to find out that a lot of biomolecules contain these phenol groups, and we'll look at those a little bit later in the semester. Alcohols, we don't really think of them as being acidic, but they do have that positively polarized hydrogen. So you have the OH group, right, and the oxygen, the very electronegative oxygen, is pulling the electrons towards itself, leaving a slight positive charge on the hydrogen. Alcohol, for example, just like water, ethanol, I'm talking the smaller alcohols here, so methanol, ethanol, there will be slight dissociation in water. So it'll dissociate into an ion and hydronium ion. Anyway, this ion here is obviously an anion, and this is called an alkoxide ion. So that's just the anion that results from the deprotonation of the alcohol. So this here would be the general form for an alkoxide ion. Those are important. We're going to talk about them later. Well, it turns out that phenols are also very slightly acidic. In fact, Ka for an alcohol is about 10 to the negative 15. So just like water, you only get maybe 1 or 2 molecules and a few billion dissociate. So, you know, very, very, very slight dissociation. So phenols also have that OH group, and so they can also slightly dissociate in water. And actually the Ka here, the acid dissociation constant, is about 10 to the negative 10. So even though they're very weak acids, they're a little stronger than alcohols and water. So again, here we see this alkoxide ion and then the hydronium ion. What's important is this. These are very, very weak acids. And what did we say? A weak acid will have a very strong conjugate base. And in organic chemistry, these would be very strong conjugate bases, these alkoxide ions, okay? So we're going to talk more about these alkoxide ions later when we get to the biochemistry portion. But I do want you to know that there is slight dissociation of alcohols and phenols in water that produces a very strong base in the form of an alkoxide ion. As I said, phenols are more acidic than alcohols and water. Their Ka is about 10 to the negative 10. That means that an alkoxide ion that's produced from an alcohol would be a stronger base than one that's produced from a phenol. Okay, I think I'm going to stop right here, and in the next video we'll talk about ethers, and we'll talk about thiols and alkyl halides. So everybody have a good night. Please practice the material and let me know if you have any questions.